Okay, here we go, section 7.8, exponential models with differential equations. Talking about the CDC, number one, the number of people, P, that are infected by the coronavirus is increasing at a rate proportional to the number currently infected. Write a differential equation that models this situation. And the phrasing of this is something you're going to see pretty often, actually. The phrase where it says the number of people is increasing at a rate proportional to the number currently infected. So the number of people that are infected is increasing. When it says that something is changing, it means we're talking about a derivative. So this whole phrase is talking about the derivative. It's increasing at a rate proportional to the number currently infected. When you see that, that means that P times K, so some value is equal to dP dt. The number of people that are currently infected is increasing at a rate proportional to the number currently infected. It is directly proportional, not indirectly. So it's not K over P, it's not K plus P. It is directly proportional. So when you see something phrased like this, this is what the equation is going to look like. Here's how we would initially write it. That's what it means. And then part two, it gives us some more information. Part A says to separate and integrate. So this phrasing means this. But what we're going to try to do is get it out of this differential phase. So again, I'll copy this down. dP over dt is equal to K times P. And we're going to split the variables. And this is something you always need to make sure you do when you have a differential equation. dP is on the left. It's on the numerator in the left. So we're going to have dP over P, divide P from the right, and then multiply to get the dt over to the right. And from black to red, we have this equation. All of the P's are on the left. If it doesn't have a P, it's on the right. And at this step, now we can integrate. Make sure you show those separation of variables. On the right side, when you integrate K with respect to T, it's going to become KT. It's an indefinite integral, so plus some constant. So there is our right side. It doesn't become K squared over 2. It's not integrating with respect to K. It's integrating with respect to T. And on the left side, with P being in the denominator, that's like P to the negative 1. This is a special case. If you were trying to raise P to the negative 1 to a higher power, it would be P to the 0, which is just 1. It's gone, so it doesn't really work. This is the ln of P. And because we're talking about this in terms of an application problem, we don't need to worry about P being negative. So at this point, I'm going to say, go ahead and drop the absolute value bars. We're just talking about the ln of P. And that's going to happen a lot of times in these application problems. I'd rather not work with an absolute value bar, and I don't have to worry about that here now. It says to solve for C, but before we do that, we want to solve this equation for P. Like I could plug in my initial condition stuff right now, but it's a much better idea to continue doing the algebra and solving for P. So to get the ln of P into a P, we're going to write this into exponential form. In other words, raise both powers like e to the power. So on the left side, if I take e to the ln of P, it becomes P. On the right side, it's e to the kt plus c. Now, we looked at this before. E to the kt, those are all variables, or e is a number, but k and t are both variables. Plus e to the c, or plus c, is e to the kt times e to the c. We could split it up like this if we wanted to. Right? The plus means you're multiplying e to this power times e to that power. But I look at this a little bit further. E is a number. C is another number. It's a constant. E to the c, it's just going to be wrapped up into calling it c. So P equals c e to the kt. So we've separated the variables. We integrated, and now we have this equation solved for P. What you're going to see very frequently in these problems is you'll be given some kind of phrase like this, where it says that the rate is increasing at a rate proportional to the number currently involved or infected, whatever. This equation is going to lead us to there. I did all the integration in the algebra. If this was a multiple choice question, I would go from the first yellow to the second yellow, and I wouldn't do all the in between. If it was free response, I'd need to make sure I show my work and how I got to this equation. The separation of variables, again, is a very big step for us. But this yellow is going to lead to the other yellow. Now, part B says to solve for C. So from this point, plug in that information. Can you plug that in and solve for C? So 1,000 is the amount that we have. That's the population we have at this time. C equals K times 0, e to the K times 0. 0 is the T value. It's the number of days we have. K times 0 is 0. E to the 0 isn't 0. E to the 0 is 1. So on the right side, we have C times 1, which is just C. In other words, C equals 1,000. We've already done a lot of this work for letter C. And again, doing it early was better than doing it later, quite honestly. So it says isolate P. We have that. And select the proper solution. So now we know that P, the number of people that are infected, is equal to 1,000 because we just saw for C times e to the KT. So we have a better equation than before. We know C, and what's going to happen very frequently is when we have an equation like this capital C value is going to be your initial condition. At t equals 0 at the very beginning, this is kind of like a y-intercept, if you will. That's going to be your initial condition. Now, part 3 gives us a little bit more information. We don't have a full-out equation here yet because we don't know how this is really increasing until it tells us on the 7th day, 1,200 people are infected. So T is in terms of days after the endemic started. So T is in days. So we're going to plug this into that equation. And the goal here is to solve for K. So 1,200 goes in for P. And 7 is going to go in for T. If you don't have your calculators out yet, you're definitely going to want to get those out because we're going to use the calculator to get some decimals for us. We're going to store some values to keep it precise on the calculator. To solve this one for K, you're going to, first of all, divide both sides by 1,000. So you get 1.2 equals e to the 7K. And hopefully you recall from pre-calculus, when you're stuck in exponential form, convert it into log form or take the log of both sides. In this case, take the natural log of both sides. So on the left, you have the natural log of 1.2. When you take the natural log of the right, you get 7K. That almost gives you K by itself. On your calculator, you're going to want to take the ln of 1.2. Then divide that by 7 to get K all by itself. So I believe that gives you K is about 0.026046, a lot of other decimals. Store that value in your calculator because we're going to use it in this next problem. This whole section isn't done yet. But for the sake of question number 3, use this additional information to solve for K. Well, now I know that my equation P, the number of people that are infected, is equal to 1,000 because that was our initial condition, times e to the K, that about 0.026 number times T. I didn't put 0.026 there. It didn't actually say to write the equation. I think it's going to be helpful for this step number 4, but K is about 0.026, is always round to 3 decimal places. Once you have question number 3 done with this equation, can you use that in number 4? And I'm expecting this value to go up. If people are spreading this virus, then we should have more people who have it than originally had it. So on the first day, we had 1,000 people. So this amount should be more than 1,000. It doesn't say right here. Normally, if this is a free response, they're going to tell you either to round it to like a number that makes sense because we're talking about people here. So do it, round this one to the nearest integer. And I think it comes out pretty close to an integer anyways, doesn't it?
Yeah.
All right, so we're going to round that one just barely up to 1367. And there we go. So this kind of phrasing is something we're going to see pretty often, like we had in this question number 1. You need to interpret that, recognize that it means this, which is going to lead to that equation. All right, let's go and turn the page, look at some of these important ideas. So if you have an equation like this, I'm going to put a double arrow, it's a biconditional. If you have an equation like this, what it means, or the way you might see it phrased to get to that equation, it might say that a rate of change of a quantity, and this one specifically, we're talking about y, so the rate of change of y is proportional to the quantity. This is a phrase you will see quite a bit. So specifically in this one, I say the rate of change of y is proportional to y. That's what this means. The rate of change is y is dy over dt or dy over dx, depending on what variable we're talking about. And it's equal to ky. It's directly proportional, so it's all going to be linear, some constant multiplied by that. This is going to be either exponential growth or exponential decay, depending on if k is positive or negative. Like in this case, we just talked about k was positive because something was growing, it was getting bigger. Sometimes k is going to be negative if something is getting smaller, it's decreasing. And as mentioned from the previous page, when you get an equation like this, which is what the phrasing is telling us, if we were to actually solve for y then, because a lot of times we're supposed to get the function, the y value by itself, we would get y equals ce to the kt, where c is an initial value. If t equals 0, capital C would be how much you have at the beginning, and kind of like a y-intercept. Lots of words. So this is math class, probably more words you've seen in any other math class before. So we have to read through the words, figure out like what's going on in this problem. Go ahead and start reading number 5. All right, so the thing about this one, it says during the first 4 weeks. The first 4 weeks, the 4 doesn't really matter. I know the number 4 is in there in answer A, and maybe you're thinking, oh, that's got to have the 4 be significant. It really isn't that significant. It's weight in grams, blah, 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 but it satisfies this differential equation. Another way of saying this is that the rate of change of the weight is proportional to the current weight. That's another way I could phrase this, Yellow. If I didn't give you this equation, it might say something like that. But when you see an equation like this, where the derivative of w is equal to w times some constant, this is a direct variation. One of these meets that form. Question A is not correct. Question A could be kind of close, but the problem with this one is we have the plus 81. This is not direct variation. You can't add a number to it. Letter B would be linear, definitely not correct. Let me skip letter C. Letter D is definitely not working. You're supposed to have e to a power. We have t squared, and the plus is way off as well. C would be the only one that makes sense. It's in that form of y equals c e to the kt. C is an initial value. The initial weight was 85 at this time. K is positive because it is getting bigger. I would have expected that to happen. But C is definitely the best and only answer that could make sense for this one. Number 6, now we have actually some numbers in this one. So let me go ahead and pause for a second, give you a chance to read it. Okay, so the first sentence, the rate at which the drug leaves the bloodstream is proportional to the amount in the bloodstream. The rate is proportional to the amount that's actually there. That's one of these differential equations that we're talking about. Normally, I would use the letters y, but in this case, they're talking about the amount that is actually there is a, so I have to make sure I use that variable. What this means to us, this yellow phrase, is that dA over dt, the rate of change with respect to time, is proportional to the amount that's actually there. That's what that yellow phrase means. Now, again, if this was multiple choice, I would skip over some steps. If it was free response, I'd have to split the variables, do the integration, and then get to this next step. I'm going to say this is probably more of a multiple choice type question, honestly. So I'm going to go directly here. Instead of saying y equals CE to the KT, what are we going to plug in for y? That's our A value. A equals C. That's the 400. That's our initial amount. E to the K times T for right now. So I know this to be true because of that yellow phrase where it says the rate is proportional to the amount in the bloodstream. I know the equation was this, and it's going to transfer into y equals CE to the KT using specific variables from this one. Now we have this. Then, after 2 hours, this much remains. So I could have, like, if I didn't know the 400 went there, I could have plugged 0 in for T. I could have plugged 400 in for the A value or the Y value. I would have got that the C, this constant, is in fact 400. I just know that that's where the initial amount's going to go. So can you plug this blue information in to solve for K? And it says that the drug is leaving the bloodstream. So I'm expecting K to be negative, because if you have 400 milligrams in your bloodstream at a certain point, it should start to dilute and become less in the bloodstream. So again, K should be negative because we're getting less of it. So can you plug that in, solve, and get the final equation? Your final answer should be something along the forms of A equals blah. Good news is T is supposed to be in hours. It says after 2 hours, so I don't need to worry about changing that into something else. Divide both sides by 400. 376.7 divided by 400 equals e to the 2k. Take the natural log of both sides. So the ln of that decimal, whatever 376.7 divided by 400 is equal to 2k. Take the natural log of that, divide both sides by 2, then we get the k value. K should be negative because the amount in the bloodstream is decreasing. K, in fact, is negative 0.03 0.30. So calculator work through this, which means our equation for A of t is 400 initial amount e to the negative 0.030 t. We're ready to move on to number 7. We're given this differential equation. Sometimes the problem will be phrased as the population is growing at a rate proportional to the current population. That's what this equation is saying. But we know from doing these problems enough that this could easily be translated into a more usable equation where P is equal to CE to the KT. I chose P because we're not using Y here. The population is P, so P is equal to this. The city's population doubles every 12 years. All right, so can I plug that in there? The city's population doubles every 12 years. Well, if the initial population is C and it doubles, then that would be 2C for the current population. E to the 12 times K, T is going to be 12 years. And the thing with the C equals 2C, divide both sides by C, whatever that original population is, and it doesn't really matter. I can make up a number if I wanted to, but we'd end up getting 2 is equal to E to the 12K. Like we've done in these other problems, once you're stuck here, then go back into log form, take the ln of both sides. ln of 2 is equal to 12K. So take the natural log of 2, that's calculator work, then divide that by 12 to get K all by itself. So my calculator, I'm taking the ln of 2, dividing that by 12 to get the K value. I need to answer the question because it's actually asking for K. So K is about 0.058. That is definitely a rounded number. Store that value in your calculator to keep it precise because we're not done with this question. Part B then asks about something else. Thank you. So then to question B, in how many years will the population triple? So I'm going to go back to this equation. I still don't know the initial population, and it doesn't even matter. If it's a small town and the population is tripling or a large town and the population is tripling, the answers to this would be the same. The population is going to triple in the same amount of time. So I'm going to go back to here again and say, all right, the initial population is C, and I want the population to triple. That means I'm going to call this 3C on the left. Going back to the right, it's E to the K. Now I have this value stored in my calculator, not just the 0.058, but the 0.05776 and all the other decimal places times T. Like we did in the last problem, then divide both sides by C. 3 equals E, which is a number, to the K, which is a number stored in our calculator, times T. Use what you know about exponents and logarithms. Can you solve for T then? So if I think about this, if it took 12 years to double, this answer better be something bigger than 12. Better be something bigger than 12. If I asked how long it took it to quadruple, I'm thinking it's going to be less than 24 years because it's growing continuously here. But it would still be something bigger than 12. But tripling, take the ln of both sides. ln of 3 equals K times T. Take the ln of 3, divide it by that value stored in your calculator, that K value. And this one, we're going to actually put it as a decimal, round to the 3 places, 19 point. So we're going to round that up to the 0.020. It's going to actually round up. This 0 is going to be a significant digit rounded for us.